Hello, welcome back to Tall Building class. Today we will learn about wind load. Create wind load by click, load. Lateral load. Wind loads. A window will pop out. Today we will study how to fill in all the fields of this panel. First of all, we need to select the corresponding load case. Here, we create a wind load in the X direction. Similar to seismic, Midas Gen provides multiple standards for calculating wind loads such as International Building Code 2012, which equivalent to American Standard for Minimum Design Loads for Buildings and Other Structures 2010. National Building Code of Canada. Eurocode 8. Indian Standard. Korean Building Code 2009. Chinese Code for Design of Buildings. In this lecture, wind load is calculated according to the American Standard for Minimum Design Loads for Buildings and Other Structures 2010. Midas Gen provides two calculation method bases on ASCE 7-10. They are alternative method and directional procedure. While directional procedure can be applied to all structures, alternative method is only applicable for structures which satisfy the following criteria. The building shall have no unusual geometric irregularity or spatial form. The building does not have response characteristic making it subject to a crosswind loading, vortex shedding, instability due to galloping of flutter, and does not have a site location for which channeling effects or futtering in the wake of upwind obstructions warrant special consideration. The building greater than 30.48 meters in height shall be limited to a height to least width ratio of 4 or less, and with a fundamental natural period less than or equal to 1 second. It is obvious that alternative method is not suitable for designing high-rise buildings. Thus, we focus on directional procedure in our lecture. First of all, we determine basic wind speed. This is determined according to the national database. Normally, the parameters are represented as contour maps. ASCE 7-10 measures basic wind speed at 10 meters above ground in an open and flat area. It is noted that wind is the Earth's atmospheric movement, so its speed is not a constant parameter. Thus the term recurrence interval is presented. A wind speed is expected to occur one time in 300 years if that speed is associated with recurrence intervals of 300 years. It is clear that a longer the recurrence interval will result in greater wind speed. This is very important in structural design because a structure should be designed with an adequate load magnitude. For example, it is inappropriate to calculate a temporary structure with the wind load that corresponds to 1000 years recurrence interval. ASCE 7 to 10 uses 3 basic wind speeds associated with a mean recurrence interval of 300, 700, and 1700 years. Each speed is designated for a group of risk category. Let's recall the concept of risk categories by some examples. Risk Category 1 – Structures that are normally unoccupied and would result in negligible risk to the public should they fail. These include structures such as barns and storage shelters. Structures in Risk Category 1 shall be designed with basic wind speed associate with recurrence intervals of 300 years. Risk Category 2 – Most common buildings and structures such as residential, commercial, and industrial buildings are considered as Risk Category 2. Structures in Risk Category 2 shall be designed with basic wind speed associate with recurrence intervals of 700 years. Risk Category 3 – This category includes buildings and structures that could pose a substantial risk to human life in case of damage or failure. Structures in Risk Category 3 shall be designed with basic wind speed associate with recurrence intervals of 1700 years. Risk Category 4 – Buildings are designated as essential facilities. Structures in Risk Category 4 shall be designed with basic wind speed associate with recurrence intervals of 1700 years. The next parameter is exposure category. However, before getting to it, we must understand the concept of surface roughness. Surface roughness represents conditions of surrounding area. According to ASCE 7 to 10, there are 3 types of surface roughness which are B, C, D. Category B – Urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstructions having the size of single-family dwellings or larger. Category C – Open terrain with scattered obstructions having heights generally less than 9.1 meters. This category includes flat at open country and grasslands. Category D – Flat, unobstructed areas and water surfaces. This category includes smooth mud flats, salt flats, and unbroken ice. Others necessary concepts are upwind and downwind directions. Upwind is the direction that the wind is coming from. Now we can determine exposure category by roof height and surface roughness. Exposure category B, for buildings with a mean roof height of less than or equal to 9.1 meters, exposure B shall apply where the ground surface roughness, as defined by surface roughness B, prevails in the upwind direction for a distance greater than 457 meters. For buildings with a mean roof height greater than 9.1 meters, exposure B shall apply where surface roughness B prevails in the upwind direction for a distance greater than 792 meters or 20 times the height of the building, whichever is greater. Exposure category C, exposure C shall apply for all cases where exposures B or D do not apply. Exposure category D, exposure D shall apply where the ground surface roughness, as defined by surface roughness D, prevails in the upwind direction for a distance greater than 1,524 meters or 20 times the building height, whichever is greater. Exposure D shall also apply where the ground surface roughness immediately upwind of the site is B or C, and the site is within a distance of 183 meters or 20 times the building height, whichever is greater, from an exposure D condition as defined in the previous sentence. Mean roof height is automatically determined by Midas from story data. In next step, we consider topographic effect. Topographic effects is wind speed-up effects of nearby hills, ridges and escarpments. Normal wind speed is smaller at the ground, but wind is speeded up when it blow through escarpment, riddle, or hill. The following inputs must be given to calculate topographic effect according to ASCE 7 to 10. First one is wind direction. Second one is shape of hill. It can be 2D ridges or valley, 2D escarpment, or 3D axisymmetrical hill. Third's input is relative position of building and hill. Next is hill dimensions. Finally, it is distance from hill crest to building. Next, we move to directional factor. This is determined based on structure type. As same to seismic load, the magnitude of wind load also depends on structure stiffness. ASCE 7 to 10 categorizes building into two classes, rigid structure and flexible structure. Buildings are classified by natural frequency. Flexible building when natural frequency is less than 1 Hz. Rigid building when natural frequency is greater than or equal to 1 Hz. Normally, tall buildings are flexible structures and hence flexible structures should be selected for wind design of tall buildings. Natural frequency of building can be estimated by formulas if the following criteria are satisfied. Building height is less than or equal to 91 meters. Building height is less than 4 times its effective length. Effective length can be computed as From now on, I will spend a few seconds for you to take a closer look at the formulas. The approximation of building natural frequency can be calculated as the following formulas. It is noted that mean roof height, h, in these formulas are measured in feet. Steel moment resisting frame buildings. Concrete moment resisting frame buildings. Structural steel and concrete buildings with other lateral force resisting systems. Gust effect factor is the last parameter. However, let's spend a few minutes to understand it before diving into calculations. Gust is a sudden and brief increase in wind speed due to its eddies. If the wind gust reaches its maximum value and vanishes in a time much shorter than the period of the building, its effects are dynamic. On the other hand, the gusts can be considered as static loads if the wind load increases and vanishes in a time much longer than the period of the building. It is obvious that gust effects become larger in a flexible building, long period or small frequency. In rigid structures, frequency is greater than or equal to 1 Hz. Gust effect factor accounts for the fact that the wind load is not perfectly coherent throughout the surface over which it acts. In flexible structures, frequency is less than 1 Hz. Gust effect factor not only account for the imperfect spatial coherence of wind loads, but it also considers addition dynamic amplification of the along wind response due to the variation of the wind loading with time. According to ASCE 7 to 10, gust effect factor can be computed as for rigid buildings, for flexible building, Natural frequency of building can be estimated by formulas if the following criteria are satisfied. Intensity of turbulence. Equivalent height of structure. Peak factor for background response. Peak factor for wind response. Background response. The integral length scale of turbulence at the equivalent height. Peak factor for resonant response. Resonant response factor. RL, RH, RB factors. Fundamental natural frequency. Damping ratio, percent of critical. Mean hourly wind speed. Basic wind speed. Horizontal dimension of a building measured parallel to the wind direction. Horizontal dimension of building measured normal to wind direction. Mean roof height of a building or height of other structure. Constant parameters depend on exposure category. Now we control load direction by wind load direction factor. Click Add to add wind load profile. Click Wind Load Profile to review load configurations. Click OK to finish. Now, let's summarize the calculation procedure. Determine risk category of building. Obtaining basic wind speed associates with risk category. Determine surface roughness class. Determine exposure category. Input topographic effect. Determine directional factor. Estimate natural frequency of building. Determine whether building is rigid or flexible basis on natural frequency. Calculate gust effect factor. This is the end of today's lecture. Thank you for your attention. See you again next week.